Who has homework questions? Anybody? We've been looking at the art gallery theorem. That's a branch of computational geometry. So computational geometry is a way of figuring out more efficient ways of doing work with geometric figures. Because it often leads to algorithms, it's often involved with computer science people. So there's lots of branches of mathematics. You don't usually see those in your high school and grade schools, because what you usually see is an algebra track that undergirds all of these mathematics. So we're not getting into that algebra that undergirds a lot of this, but that is what you need, that algebra track, if you're going on and studying these areas as a foundation. And so we're just looking at the highlights of these areas. So one of the results we're looking at is the art gallery theorem. We'll go ahead and take a look at that again. So the art gallery theorem said if we have a polygonal closed curve in the plane with v vertices, then there are v divided by 3 vertices from which it is possible to view every point on the interior of the curve. If v divided by 3 is not an integer, then the largest number of vertices we need is the biggest integer less than v divided by 3. We are able to see every point inside from less than or equal to v divided by 3 vertices. So I had each of you make polygonal closed curves, and then look and see the most number of guards you would need to see every point inside that polygonal closed curve. And indeed, we had two people make polygonal closed curves with 7 vertices. And with the designs they made, the most they would need on one of those designs was 2, and the most they needed on the other was 1. So the art gallery theorem tells us that the most you'd need is 2, because the 7 divided by 3 is 2.3, and sure enough, we saw that board out. So this is an upper limit. This is the most you would need. And we saw that, for example, 2 different people made polygonal closed curves with 8 vertices, and one design called for 2 guards, and one design called for only 1 guard. And the art gallery theorem says the most you would need would be 2 guards, because 8 divided by 3 is 2.7. So we have an upper limit when we look at the art gallery theorem. And now we're going to see, well, why is that? Now, the art gallery theorem was proposed a while back in the mid-1900s, and proven by Chvátal. So it's proposed. The theorem was proposed by another person named Klee, and then it was proven by Chvátal. I'm probably slaughtering that name. Anybody know enough French to pronounce that properly? Okay, that person. But the person who gave us a beautiful, elegant proof is right here, Professor Steve Fisk. His proof is so beautiful it got included in a book on elegant proofs. So here's what happened and how he figured it out in a nice, succinct way. Creative ideas can arise anytime and anywhere as long as our minds are open. This is your textbook, by the way. The story of how Steve Fisk came up with the idea for his proof is a wonderful and funny real-life illustration of this maxim. Here Professor Fisk recounts the episode. Here's a quick story. My wife and I were traveling across Asia during 1975 to 1976, and during our 1-month stay in Iran, I visited the math library at the University of Tehran. I read Chvátal's article, or rather I looked at it, for the proof seemed so complex that I didn't want to read it. I did like the result, though. A few weeks later, we were traveling on a bus between Herat and Kandahar in Afghanistan. It was hot, dusty, and noisy with squawking chickens on the roof. I was thinking about it. Well, I was probably dozing off, actually, and I thought of the proof. This is how people who do research in math think. I had breakfast with one of our professors who's no longer here because he's retired, Professor Hugh. So he and I had breakfast with a math candidate, Mary Guy, who's a lecturer here now, but she was applying for the job, and we didn't know each other. Well, I knew Professor Hugh, but neither of us knew this person applying for the job, and it was so hard to make conversation. Have you ever been in a situation like that where nobody will talk? And there's things you can't ask a candidate because of privacy laws and such. So I'm just plugging away, trying to make conversation, and Professor Hugh's just sitting there leaning against the window, staring out the sky. I just could have kicked him, you know. But later on I asked him, what were you thinking about? And he said, well, I was thinking about a research project I'm working on. Okay, all's well that ends well. Well, this proof that Stephen Fisk gives us is beautiful and elegant and helps us understand the theorem. So we're going to look at his proof. Wikipedia is a fairly good place to look at mathematics. So here on Wikipedia, I have just looked up the art gallery problem. And we see Fisk's proof. It's so short and elegant, it was chosen for inclusion in proofs from the book. The proof goes as follows. Okay, so here's an example that we're going to use as we look at this proof. This is a polygonal closed curve, right? But it's also been cut up into pieces. So first the polygon is triangulated, and that's what Fisk has an example of here, or Wikipedia rather. They've cut this up into triangles. And then the triangles are colored in 3 different colors. So I colored green, blue, and yellow. And you can always, since there's 3 colors, you can always get that green, blue, and yellow on one of your triangles without having to use one color twice. Under a 3 coloring, every triangle must have all 3 colors. The vertices with any one color form a valid guard set, because every triangle of the polygon is guarded by its vertex with that color. Since the 3 colors partition the end vertices of the polygon, the color with the fewest vertices defines a valid guard set, with at most n divided by 3. So that's where the number of vertices divided by 3 comes up, because we split the polygonal closed curve up into triangles. And then, well, let's just try a few examples. Okay, let's try a few examples. So we're staying in 4.2 with the art gallery theorem, and look at a triangle. Okay, so draw whatever kind of triangle you want. If you had a triangular polygonal closed curve art gallery, how many guards would you need if they're standing, if they're only allowed to stand at the corners? How many guards would you need? 1. Yeah, just 1. You can see that. In fact, it wouldn't even matter which corner the guard stood at. A guard at any corner can see the whole triangle interior. So that's what Stephen Fisk based his proof on. We'll make just a little simpler example about there we go. We could have used a square, but a square is pretty simple too. So we'll go up to 5 sides, 5 vertices, 1, 2, 3, 4, 5. So we'll cut that up into triangles. Just by connecting vertices. So only connecting at the corners, don't connect in the middle of one of the line segments. Connect at the vertices to form triangles. I'm going to connect here to here in case this looks like a straight line, but I didn't use a straight edge, so it may not be a straight line. So I'll connect one more here, okay? Now, at any point of any of these triangles, the guard can see inside all of those triangles. I don't know if I phrased that right. So in this bottom triangle, you can put a guard at any point on this bottom triangle here, 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 and the guard can see the whole triangle. If the guard is at this corner, the guard can see this triangle and this triangle because the guard is on this triangle. If the guard's on this point, then the guard's on the point of all three triangles, and so the guard can see inside all three triangles. Well, the idea that Fisk had about coloring the corners was to help you make sure you get the least number of guards that you need by making sure you're putting guards on the corners where they can see a sufficient number of triangles to make as least number that you need. So we'll just write red, white, and blue. It's easier than trying to color, okay? So just take one of your triangles and label it red, white, and blue. Okay. So I'll pick the top one. Now once you've colored one of your triangles, it helps you tell what color to do the next one. So I have white and blue on this line for this other triangle, so that means this other triangle I put a red here. Okay, don't go right to the triangle where you only have one color on the vertice. Go to the one where you already have two, so that you keep your colors correct. Okay, so I go to this one next because I have the white and the blue. Now I have red and blue, and that means this one has to be white. So I've now colored all the vertices. I have 2 red, 2 are white, but 1 is blue. So where the 1 is blue, that's where I want to put the camera. Because where the 1 is blue, that's the least number of vertices that I need to see all the triangles. Now we worked that out by hand before we did the actual coloring. The coloring is helpful when you have more complicated drawings. So once you get the triangles done, then if you color your triangles vertices, you color the triangles vertices, see which vertice has the least number of colors. And then that's where you would put your cameras. Now there's other ways. I mean, when we go through this method, it's not always the only way, but it's a way that always works. Notice the art gallery theorem would tell us that 5 divided by 3 is 1.7, so 1 guard, and that is in fact what we found. So at most 1 guard, and that is what we found. Well, if you still have your polygonal closed curve that you sketched in class on Monday, you can try this with that one. We're going to try with some that are all the same, just so that we can all work together. So I brought some to hand out. Online students, you can print this off the class activity materials. So here's some polygonal closed curves, and we're going to go ahead and work on those together. This is, by the way, one of these would be a type that would be a problem on a quiz. Your quiz would say, demonstrate your understanding of the art gallery theorem by triangulating the polygonal closed curve, coloring the vertices, and circling where you place the cameras. Maybe we should write that down so you know what to expect. Okay. Demonstrate your understanding of the art gallery theorem by triangulating curve, coloring vertices, and circling where you would place the cameras. Oops, I don't think you have an E in circling. So where to place guards or cameras. I'll just say guards here. Usually I put some lines where you can tell how many colors of each camera you have so that it makes it a little easier for me to check your work too. Okay. So cameras, so I'd make a line where you can list the total vertices and how many would be red, white, and blue. Now that's going to differ from student to student because there is more than one way to do this. So that's why I would check these by hand. Okay. So we're going to go ahead and triangulate one of these. So if you have a straight edge, please take it out. If you don't, please use your student ID. Where's my straight edge? So as you're doing this, remember, only connect vertices. Only connect vertices when you're making these triangles. Don't cross lines in the center. So don't cross lines as you're making these triangles, okay? So just pick out two corners and connect them. I was just going to start at the top, but that's, again, not the only way to do this. But it's a way. So just connect two vertices. If you've made a triangle, then you're done with that one area. I didn't make a triangle below, so I'm going to make another line. And I'll connect here. So that time when I connected two vertices, I didn't make any triangles. But that's okay, I can keep going, right? I'll connect here and here, and that will make a triangle. So only connect vertices. Don't cross lines at all on the inside. So the idea is that we're getting triangles because any point on a corner of a triangle allows you to see any point inside the triangle. So if you're at any of the corners of the triangles, you can see inside all of that triangle. So just connect on the corners and don't cross lines as you're sketching these. Okay, so now let's color red, white, and blue. It doesn't matter how you start, but once you start, only go forward on the triangle that you have two colors with. So for example, here I put red at the top and white and blue here. On this line, that line is shared by this triangle. So I'm going to go to this corner next. I'm not going to go over to here where I only have one color on the triangle. Stick to where you already have two colors. Otherwise you're going to all of a sudden get to the end and you'll have to put two whites together on one triangle. Okay, or something like that. White and blue, so this corner is red now. Now look at the triangle you have two colors on. Which one is it? This one. Okay, I have red and blue, so that means this corner has to be white. Now there's, look again and see which triangle do you have two colors on. I have blue, white, this one has to be red. Or I have red, white, this one has to be blue. Okay. So always move forward to the triangle you have two colors on. So white, red, this one's blue. Red, blue, this one's white. Red, white, this one's blue. White, blue, this one's red. So once you pick a triangle and color it, you've also colored two corners of another triangle. Go to that triangle next. Okay, well let's keep track of the total number of vertices, and then how many we did red, how many we did white, and how many we did blue. See, so total vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think there's 11. Let me remember this time where I started. Yeah, 11 vertices. Okay, so the art gallery theorem tells us the most guards we should need is 11 divided by 3, which is 3.7. So I shouldn't need more than 3. Well, let's see what we have here. How many red? 1, 2, 3, 4 reds. Whites. 1, 2, 3 whites. Blues. 1, 2, 3, 4 blues. So there's 11 vertices altogether. 4 are red, 4 are blue, 3 are white. So that's where I put the cameras, at the white ones. So then we circle the W's. And of course they'd be inside the gallery, not outside, but the W's didn't fit inside very well. So that's where I put the cameras. So notice this camera can see up into this triangle and this triangle and this triangle. Now it can see further too, but it has these 3 triangles covered. This camera has these 4 triangles covered. This camera has these 2 triangles covered. So the art gallery theorem proof helps us figure out where to put the cameras. Let's go ahead and do another one, okay? Let's do this one. Anybody have any questions on the first one? Okay. All right, so I'm going to connect these 2 corners to make a triangle. And then I'm going to connect these 2 corners to make a triangle. And I'll connect these 2 corners to make a triangle. And there's more than one way to do this. If you're going to do it a little differently, that's okay. And just keep making triangles by connecting corners. Make sure none of your lines cross, and you only draw to the corners. So this is the way I've made the triangles. As I said, there's more than one way. And now I'm going to pick one to color red, white, and blue. So I just picked one to color red, white, and blue to get myself started. But once you've started, now you go to the triangle that has two colors assigned on it already. Okay, so this triangle has white and blue, so I'm going to put red down here. That gave this triangle two colors, white and red, so I'll put blue over here. Since I have red and blue here, I have to put white over here. Now I have red and white, so I'm going to put blue here, white and blue, so I'm going to put red. I have white and red already, so I put blue. So I will go ahead and count how many I have altogether. I'm going to start up here. I better put a dot. Okay. 9 vertices. 9 vertices. So the most I should need for cameras is 3. Let's see how this particular triangulation worked out. So for red, there's 1, 2, 3 cameras. For white, there's 2 cameras. For blue, there's 1, 2, 3, 4 cameras. So the arc gallery theorem says the most I need is 3. In this case, I can actually use 2. Put one here and one here. So this one sees up into these triangles, and this one sees these 4 triangles. And actually, they have some overlap too, don't they? Well, I always want you to be able to feel like you know how to do quiz questions. Well, so I'd like you to do the next 2. Can you please work them out, and I'll come around and see how you're doing. Remember the biggie when you're coloring these, so you don't want to get to the end and say, wait, now I have 2 red cameras on one triangle. You don't want that to happen. So once you pick a starting triangle, go to the next triangle that has 2 corners already colored. If you're stuck, raise your hand, okay? Or did you do it a little differently?
I did it like differently.
Oh, that's okay. Yeah.
So,
You still got 3, which is less than 9. Less than.
which one would it be though?
Either one
Could
is
be either?
fine.
Okay.
Yeah. Either one is fine on a quiz. There is one way to do this. Just so your number comes out to be vertices divided by 3 or less.
Okay.
Put a camera there. Yeah. Colors come out right. Just take 2 corners and connect 2 corners, and that should help you get going. So Sure. Yeah. And so you'll either have made a triangle or not. And if you haven't made a triangle, then you'll have to divide some more. Okay, so this, you're right to go to this one because you have two colors on it. Exactly. You have blue up here. Yeah. Okay, so you connected these two. You connected these, you connected these. Okay, so you connected these. So here I have a triangle, 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 triangle. You need to connect two corners into your yeah, so it's always connecting corners. Yeah, you can do it like that if you want to. Okay, so that made a triangle. Now, this is a triangle, so you have to do two corners again. You started on carbon. Yeah, now you have a triangle. Triangle, triangle, triangle. Yeah, you did. You started on carbon. Yeah. Okay, so pick one of the color out there. Pick one of the color with what you like. They can. They don't have to. Well, let's see. You have a triangle. Okay. Okay, so you have red on the blue, white, and that gives you, so you have the red there. And white and red, so you have the blue there. Oh, I see. Now you don't have. Yeah, so it's going to be over here. We'll try one and see how it goes. Well, you can do that. You can make more triangles if you want, if that would make it easier. So you could try coloring it. Yeah. You're right. You will make more. I think you might have. Oh, yours. I think yours will work out better. So we have red, white, and blue. And so, you know what? I think you might have to make another triangle up here.
Yeah, that one is.
I think I made that one. Never mind. I did that originally. I made that one.
Okay.
So you started on the harder one. But that way, okay, now you have white and blue. So what color is this one? Yeah. Okay. And then I think you should have a blue one here also. Okay, so now we have blue and red, so we'll finish this one. And that actually works out really well. You might have to do that over here. Okay, how would you go ahead? So when I get you another paper. Does anybody else want another paper? Anybody want another paper? Okay. Oh wait, this one has two whites still. Oh, you know why? This one's kind of tricky. If you make another triangle in here.
Oh my goodness.
Yeah.
Yeah.
Yeah, that's what I did. Yeah, because otherwise you so then so this is the thing, right? Because then you won't have duplicating colors. Okay. Or you're going. Just put a different triangle.
This one?
You can see that
So I need to
triangle.
plug in with these triangles?
Yeah, it actually, it doesn't look like that. It's a lot of triangles. Because otherwise, look at all the different colors you have on that one shape.
Yeah, I just did those, I did those all those others.
Yeah, that might change your colors.
Oh, I know
How
why.
did this one go?
I think this one was one. But the one was one.
Because these aren't vertices.
Oh, and you started on the harder one. This one's easier.
Okay.
Oops. And here's the- Oh yeah, that looks very nice because they did these types of colors. That's what I do on the quiz. Yep, we did that.
I'll just go ahead and sketch these out. So just keep connecting vertices until everything is triangles. Nothing should be left that's not a triangle. Triangles have 3 sides. Once you pick a triangle to identify colors on, then you're stuck with those colors. So this white, blue, this has to be red. White, red, this has to be blue. White, blue, this has to be red. Red, white, this has to be blue. One, two, three, four, five, six, seven. So the first one was a little easier. It only needed the one camera. This one's harder. There's more than one way to do it, but you pretty much make a whole bunch of triangles in the bottom. So if you don't make a triangle here in this little tiny skinny space, then you get some troubles with colors later. So if this one took you a couple tries, that's not surprising. It's a little tricky. Whoops, that's supposed to go to the corner here. So making many triangles on the bottom here allows you to avoid problems with the reds and whites and blues not coming out correctly. So now when I say red, white, and blue, this is red and blue, so I have to have white in this bottom corner. Now this is blue and white, so this needs to be red. This is blue and white, red and white, so this needs to be blue. Blue and white, so I have to have red. Red and white have to have blue. Blue and white, this needs to be red. Red and white needs to be blue. Red and blue needs to be white. Red and blue needs to be white. And again, there was more than one way to do this, but you should have all triangles, and you should have a lot of triangles in the bottom there, so that you don't have these like random cameras only at the one vertice. a quick check is to make sure your red, white, and blue cameras add up to the number of vertices, because there should be a camera at each vertice and not two cameras at any vertice. So the sum of your red, white, and blues should equal the number of vertices. So this one needed 4 cameras, regardless of which corners you pick. I'm just going to pick white because they're easiest to circle, but you can pick another color. The art gallery theorem actually has quite a few modifications where people look at different variations of the art gallery theorem. Do you have any questions before we move on to look at those ideas? I thought we'd point out the life lesson in this section. Often in life, hard questions have answers that are made up of many easy pieces, and that's the case here. When we take Steve Fisk's triangulation of those more complicated curves, we can make simpler triangles that are easy to find security guards for than a big, complicated polygonal closed curve. So if you are interested in geometry, you might want to look at the variation on the art gallery theorem that has to do if all your walls are mirrored. So visibility within a house of mirrors question is in your textbook. For an arbitrary polygonal closed curve having mirrored sides, must there exist a point from which every point inside the polygon curve is visible? So we can see a point here that works. For example, if you put a camera here and the walls are all mirrored, then you could see all the way down into this corner because the walls are mirrored. If you put a camera here, you can see all the way up into these corners and this corner because the walls are mirrored. But the question is, can you do that for any polygonal closed curve? Will there always be a point? And that is an open question. So somebody is undoubtedly working on this computational geometry problem and will come up with an answer, but we don't know yet. Is it true for all of them? When it hasn't been disproved yet, that means that for every polygonal closed curve they've made so far, there's been a way to place the camera to see the mirrored surface. So all it would take to disprove this and say, no, it's not possible, is a counterexample, and nobody's come up with that yet. We're going to go on into the next section. Hopefully you brought a compass with. Do you have any questions? Oh, here's a reminder. Study groups tonight, okay? So study group would be a good thing to go to. Get some practice at this. I am sure your tutors can make some polygonal closed curves for you to practice on. I brought a poem about compasses because I asked you to bring a compass. Who knows a famous poem about compasses, or who's heard one before? Anybody? I was actually an English minor in college. I really like reading. So here's John Donne's book, Valediction Forbidding Morning, and it talks about a compass. It's just so, he's comparing these two people's love to a compass. If they be two, they are two, so as stiff twin compasses are two. Thy soul the fixed foot makes no show to move, but doth if the other do. And though it in the center sit, yet when the other far doth roam, it leans and hearkens after it, and grows erect as that comes home. Such wilt thou be to me, who must, like the other foot, obliquely run. Thy firmness makes my circle just, and makes me end where I begun. Now, who wouldn't like to hear their lover say that to them, huh? I think if I said that to my husband, he'd be like, what? But I think it's beautiful. All right, so we are going to need compasses here, and it's fitting that I brought a poem because we're moving into the area of art. We're looking at beautiful rectangles. We're going to imagine the ideal shape that comes to mind when you hear the word rectangle. And draw the shape on this page and initial your rectangle. Well, we're not going to draw it. Instead, we're going to have you vote. So I'm going to pick some out of the textbook for you to vote on. So your author calls this the section the sexiest rectangle. And we have some different rectangles to vote on which one you like best, okay? So we have the square. I drew that one in because your author didn't have a square. And then we have rectangles varying by proportion. So we have some that are quite short compared to how wide they are. Some that's not quite a square but is taller than this one. This one I think is wider compared to its height compared to this one. And this D looks very similar to C except it's put on its side. So vote, go ahead and vote and see which one you think is most appealing to you. Because the idea in this section is that there is in fact a particular rectangle that appeals to people in general, and you see it show up a lot in art. Because of Future Phoenix, we have a kind of small class here today, so we won't have as many people voting as we do usually. Okay, how many people like, I'll go in order on the paper here. How many people like E best? Raise your hand if you like the square best. Okay, one of those. And again, this is subjective. It's not like there's a best answer. How many people like A best? Okay, one of those. How many people like B best? 1, 2, 3, 4, 5 of those. How many people like C best? One of those. And how many people like D best? One of those. Okay. So we had a pretty even spreading about these four, but B took the prize. Now what we're going to be looking at in this section is proportions. What makes a rectangle shaped differently is its proportion. So let's take out your rulers and measure these and find their proportions. If you don't have a ruler, this is going to be hard to do. Oh, you know what? I forgot to have you take your class activity photo too. So let's look at your class activity photo. That would be for this work that you did here. Okay, can you take a picture of that? So this is the 4.2. The 4.2 class activity. And I would upload it right away because sometimes students get the wrong pictures because they're not due for a while and so they wait. So if you can upload it right away, I would do that. So the proportions would be the width to the height. So I'm going to use centimeters because those are so much easier to work with when you're doing this. So we have 2.5 by 2.5 for the square. And I'll put the long side to the short side. You can go the other way around, but I'm just going to be consistent and use the long side to the short side. So here we have 2.8 to 0.7. So that's 4. And that means that this rectangle is 4 times as wide as it is tall. The ratio here of 1 means the length and height are the same. Here the width is 4 times the height. So the favored one in today's class, 2.8 to 1.8. Where's my calculator? $1.6. So almost like a little more than 1.5 times as wide as it is tall. See, we have 2.5 to 1.2. So two times as wide as it is tall, or the other way around, 2 times as tall as it is wide. This one's 3.2 to 1.5. So this was 2.1. So a little bit more than twice as wide as it was tall. Well, we're going to be looking at which proportion is generally preferred in artwork, and we'll see that it is in fact the one that the class preferred. Again, it's a subjective measure, but we will see that show up a lot in artwork, and we're going to look at that more closely on Friday. Don't forget your compass on Friday, okay? I'll see you on Friday. A graph paper and a ruler would help too on Friday, okay?